For decades, Neptune remained an elusive mystery in the distant reaches of our solar system. It was a dim blue world, hidden behind immense distances, veils of ice, and a glaring lack of detailed data. Ground-based telescopes could offer only fleeting glimpses into its turbulent atmosphere, their observations blurred and obscured by Earth's own atmosphere. Even the legendary Voyager to flyby in 1989, while historic and groundbreaking, managed only to graze the outer surface of Neptune's secrets. Since that time, astronomers had waited patiently, optimistically for a tool powerful enough to pierce the icy layers and bring real clarity to this remote planet. That long-awaited tool arrived in the form of the James Webb Space Telescope. With it came Neptune's most detailed observations to date, observations that shattered old assumptions and unveiled a planet far more dynamic, intricate, and surprising than anyone had ever imagined. When the James Webb Space Telescope turned its infrared instruments toward Neptune, what it revealed stunned the astronomical community. The familiar smooth blue disk we had grown accustomed to from Earth-based observatories and earlier space missions was gone. In its place stood a wildly textured world marked by swirling icy haze, complex atmospheric layering, and bold, sharply defined storms, features previously invisible to the human eye. Using its powerful near-infrared camera NIRCam, Webb didn't just refine our image of Neptune, it redefined it. The clarity was astonishing, especially considering the planet's vast distance from Earth. Among the first of many surprises was the revelation of Neptune's ring system. Though the existence of its rings had been known since the late 20th century, they had remained faint and indistinct, barely visible even through the Hubble Space Telescope. Webb's infrared sensitivity and expanded wavelength range brought them into focus like never before. The rings appeared sharp, radiant, glowing like etched halos suspended in the dark canvas of space. Their clarity stunned researchers and offered the most intricate look yet at their composition and structure. These weren't just visual marvels. The detail hinted at ongoing dynamical interactions between ring particles, nearby moons, and Neptune's magnetic field that had previously gone unnoticed. But perhaps even more striking was what Webb discovered within Neptune's atmosphere. Long thought to be a relatively uniform blend of hydrogen, helium, and methane, Neptune's atmospheric composition and behavior turned out to be anything but simple. The telescope's infrared imaging peeled away the uppermost cloud layers and revealed deeper, more volatile storm systems, as well as massive vertical circulation patterns that stretched across hundreds of kilometers. These discoveries challenged long-standing meteorological models. Instead of a cold, inert planet governed mostly by inertia, Neptune revealed itself as a place of unexpected atmospheric vitality and complexity. The temperature distribution across the planet particularly shocked scientists. Previously, it was believed that Neptune exhibited a smooth gradient of temperature, cooling predictably from equator to pole. But Webb's data showed something different: thermal anomalies. There were unusual warm regions near both poles, and even areas of surprising warmth near the equator, places once thought to be much colder. These findings suggest the presence of unknown mechanisms of heat transfer, or perhaps an internal energy source that has not yet been fully accounted for. New questions emerged. How does heat escape from Neptune's core? How does the planet respond to solar radiation, despite its immense distance from the Sun? And does Neptune's magnetic field play a more active role in regulating heat than once thought? Even more intrigue came from Neptune's south pole. Webb uncovered a peculiar brightening in this region, an intense infrared glow that had only been hinted at in past observations. Now, it stood out boldly. The south polar region wasn't just reflecting sunlight, it was radiating heat from within. This suggested a localized process of convective upwelling, or perhaps a distinct interaction between atmospheric flows and the magnetic field. The implications are far-reaching. Neptune's energy doesn't escape evenly across its surface. It may instead be channeling energy out through particular polar pathways, a process potentially tied to long-term seasonal changes or climate cycles unique to planets in the outer solar system. Another captivating detail revealed by Webb was the abundance and behavior of high-altitude methane ice clouds. These delicate, wispy clouds, which form in Neptune's frigid upper atmosphere, reflected infrared light in brilliant streaks and arcs across the planet's face. Unlike water clouds on Earth or the ammonia clouds seen on Jupiter and Saturn, Neptune's methane clouds exist in far colder, more exotic conditions. Webb's observations captured their movements and clustering with a level of precision before achieved. Interestingly, their placement wasn't random. These clouds appeared to congregate around storm belts and the long latitudinal bands, suggesting a tight interplay between Neptune's rotation, atmospheric dynamics, and possibly gravitational forces from its moons. Speaking of moons, Webb's observations also offered a fresh look at Neptune's largest satellite, Triton. Though Triton was the subject of a separate detailed study, it couldn't help but steal some of the spotlight. In Webb's infrared images, Triton appeared brighter than Neptune itself. Its surface, coated in highly reflective nitrogen ice, glittered in the telescope's view, drawing immediate attention. This unexpected brilliance hinted at a surface rich in complex chemistry, possibly influenced by seasonal nitrogen geysers, or even subsurface geological activity. Triton, once thought to be a frozen relic, now looked more like an active world, one that might harbor a subsurface ocean and still be geologically alive. Webb's astonishing resolution didn't just provide snapshots. It allowed scientists to track weather patterns on Neptune in real time. Over multiple exposures, subtle shifts in cloud formations and storm shapes were clearly visible. This dynamic view opened the door to building an active meteorological model of Neptune, a feat that was once unimaginable. For the first time, storms, cloud belts, and temperature variations could be observed evolving, allowing for continuous atmospheric monitoring. And this isn't just important for understanding Neptune. These insights help refine models of exoplanetary weather, especially for distant worlds with similar compositions and climates. Even more exciting is how these new findings are reshaping our broader understanding of Neptune's role in the solar system. Previously, Neptune was considered a relatively simple ice giant, a ball of gas, and ice quietly orbiting the Sun. But Webb's observations suggest otherwise. Neptune may be more accurately described as a complex hybrid, full of dynamic processes, layered energy exchanges, and multifaceted interactions between its rings, moons, and atmosphere. These revelations are prompting scientists to revisit fundamental questions about how gas giants form and evolve, especially when comparing Neptune to its planetary sibling, Uranus. Despite their similar size and composition, Webb's data hints that Neptune may have a more active core or a very different evolutionary trajectory. Why Neptune appears to be so much more thermally active than Uranus is now a pressing question, and one that Webb may help us answer. This newfound understanding of Neptune also has direct implications for how we view exoplanets. Many of the exoplanets discovered around other stars fall into the same mass and size category as Neptune. Until now, models of these distant worlds were built on assumptions derived largely from our limited knowledge of Neptune and Uranus. But if Neptune is this dynamic, this active, and this thermodynamically unique, then it stands to reason that many Neptune-like exoplanets may also be far more complex than previously believed. This could alter how we assess their atmospheres, their potential for atmospheric escape, and even the possibilities for habitability on orbiting exomoons. What's perhaps most extraordinary, that Neptune manages to display such energetic and complex behavior, despite receiving so little sunlight. Positioned over 30 times farther from the Sun than Earth, Neptune should, by all expectations, be a frozen, sluggish planet. And yet, it boasts weather patterns, storms, and temperature variations that rival those of Jupiter, a planet much closer to the Sun. This suggests that Neptune possesses a powerful internal heat source driving much of its activity. Without Webb's deep infrared insight, this internal engine might have remained hidden indefinitely. This internal heat, and the way it interacts with Neptune's layered atmosphere, may also hold keys to understanding how giant planets sustain themselves over billions of years. The findings extend even further into the study of planetary magnetospheres. Neptune's magnetic field is unusually tilted and offset from the planet's center, creating an asymmetric and highly dynamic magnetosphere. With Webb's data, scientists may now be able to correlate atmospheric features with magnetic patterns, potentially revealing how electromagnetic forces shape atmospheric flows. In Neptune's case, some weather systems may not be driven solely by thermal dynamics or rotation, but by complex magnetic interactions, a trait that would set Neptune apart from every other planet in the solar system.